So besides being cool geometry, having a tangent plane to the graph of a function gives us a way of approximating that function at nearby places to its point of tangency. Just like in single variable calculus, if I have a function whose derivative is continuous, its tangent line is going to be really, really close to the graph itself, near the point of tangency. And so occasionally it might be useful to use the tangent line in place of the perhaps really complicated original function to approximate values of that original function at nearby points. And we can do the same thing with tangent planes to multivariable functions. So we're just going to get a little bit of practice with that. The authors of the book go into much more detail than I'd like for us to. But you know, the idea again is that if I have a curvy graph, that the tangent plane, which is flat, is really close to that curvy surface at points that are nearby to the point that we picked for tangency. And since when you found equation for a tangent plane just a minute ago, you found it with the z solved for by itself, and it looked exactly, in fact, like this equation that's being shown right here, right? If we think of that tangent plane as being the graph of a linear function of x and y, then that linear function is what we would call the linearization of the function f of x and y, near the point x naught, y naught. And so if you ask me a question about the value of f nearby the point of tangency, I can get pretty close to that by finding the value of this linear function nearby to that point. So in this next activity, I'm only going to have us do part A for today. We have kind of a, you know, not too complicated, but complicated enough function, x over x squared plus y squared. We have a point 1, comma 2. And the idea is maybe finding the value of the point of this function at 1, comma 2 is not so hard, right? We can find a tangent plane and therefore a linearization function whose graph is the tangent plane. And then we want to use that linearization to estimate the value of this function at a point that's nearby to 1, comma 2, in particular, the point 0.8, 2.3. And when you do this final calculation to estimate this value, I'd like for you to sort of show all of your steps, like show plugging in this x and y value before you do the simplification to find that z value, because I think we're going to get some additional mileage out of that at the end of the day. So anytime you're using a linearization, the roadmap is just find a tangent plane. Linearization is nothing more than a function whose graph is the tangent plane. So find the tangent plane, solve it for z, which is something that we've already done. In fact, you did it as part of the end of our last activity, as we were discovering the general principle that an equation for a tangent plane to the graph of a function can be z equals f evaluated at the point in question, plus the x partial derivative of f at that point times x minus x naught, plus the y partial derivative at that point times y minus y naught. One of the interesting things about that, before we start with this linearization problem, is that we could, if we wanted to, re-envision this thing as a dot product of a vector whose components are the x partial derivative of f, comma, the y partial derivative of f. Right? Package those together, take the dot product with a vector whose components are x minus x naught and y minus y naught. So this is just kind of a neat little elegant way to think about what these two terms that are part of this linearization kind of stand for. They stand for a dot product of a vector whose components are the x and y partial derivatives with a vector that measures the displacement from an arbitrary point xy to the point x naught y naught at which we took our linearization. So there's something very satisfying about that formulation because it looks an awful lot like the equation for a tangent line in single variable calculus. It's the value of the function at the point in question plus something that looks like a derivative multiplied by something that looks like a displacement, x minus x naught. Just that multiplication is taking the form of a dot product in this example. So that's just a little preview of stuff that's going to come up in our next class and the class after that as well. But let me hand the floor back to you with your team to work on just part A of activity 10.4.3 to estimate the value of this function at 0.8, comma 2.3 by using a linearization of it at the point 1, 2. All right, so having done this linearization problem, I think the thing that I want to point out for us to pay extra attention to as we get ready to move on is that when we take a linear approximation for a multivariable function, what we're really doing is kind of multiplying each of our partial derivatives, which kind of represents an instantaneous rate of change in the x direction and the y direction, respectively, at our given point. We're multiplying that instantaneous rate of change by an actual amount of change in the x direction, right? That's what x minus 1 does. When you evaluate this for x equals 0.8, what we're doing is we're moving away from our original point by a small distance. The small distance away from our original point that we're moving is 0.8 minus 1. And so a way to think about what we're doing here, right, is that we're taking a step of negative 0.2 in the x direction. So we're moving a distance of negative 0.2, or a distance of 0.2 toward the negative x direction, away from the point whose value we know for sure. So we know for sure the value of the function at 1, 2 is 1/5, right? And so what we're doing here is we're taking a small step to the left in the x direction, and we're also taking a small step, it turns out, north, if you like, in the y direction. We're going 0.3 up in the y direction. So one way to think about what these numbers here are kind of telling us is that that's our actual amount of change in x and our actual amount of change in y. And so I'm going to kind of replace those here. Rather than using equation editor, I'm just going to get lazy and copy a delta out of Unicode and drop it in there. So this is the change in our x variable, and this 0.3 is the change in our y variable. Right? And so when we're finding a linearization, what we're doing really is we're just changing, maybe another way to say this, right, is to subtract this 1/5 from both sides. And what I have here is the z value of my original function, the difference with the z value of my linearization. And so another way to think about that left-hand side is that that's really delta z. Delta z is the x partial derivative times delta x plus the y partial derivative times delta y. That is the very spirit of what linearization is and how it works. And so what we're going to be able to do with this next is to use this idea of linearization in our quest to figure out what a chain rule should look like for functions of several variables.